Hi, I'm Glenn. I'm an undergrad at UCLA, and today I'll be presenting a couple of results on deterministic graph coloring that I worked on with my co-authors Sepehr Assadi from Rutgers and Andrew Chen, who is a PhD student from Cornell. So to start with some background, the problem we're working on is going to be graph coloring. So we're coloring the vertices of a graph. We're assigning colors 1 through C so that adjacent vertices get different colors. And so here's an example of a graph coloring. Okay, and for some notation, n is the number of vertices, and we're going to have delta be the maximum degree of the graph. The model of computation we're using is the semi-streaming model. And in this model, the idea is that the input graph is larger than this memory you have on your computer. So you know that the vertices will be 1 through n, but you don't know what the edges will be, and they come in a stream. So that means, well, there's going to be up to n squared of them, and the idea is that your memory is going to be around O tilde of n. So the tilde here is hiding log factors. So you have around like n polylog n memory. And the idea is that after seeing the stream of edges, you have to output your answer. And then the reason why we chose like O tilde of n is because typically your size of your answer is going to be around that. So for example, with coloring, you're outputting a coloring, which is an assignment of a color to every vertex, and then that is something that takes O tilde memory to O tilde n memory to output. Okay, great. So what is known about graph coloring in the semi-streaming model? Well, approximating the minimum number of colors is quite intractable. So this is not surprising because it's NP hard anyway, right? So the main focus is going to be on combinatorially optimal colorings. So these are things like delta plus 1 colorings, or colorings based off other properties of the graph like the verbosity, or if you impose some additional restrictions to the graph like triangle freeness, you can get some better bounds as well. But the main idea is that these are colorings that you know exist for the graph because of mathematics. But the hard part computationally is to find out what is the coloring, so to come up with an example of such a coloring. So to review delta plus 1 coloring, how do you find the delta plus 1 coloring of a graph? Well, so not in streaming, just normally. What you can do is just use greedy algorithm, right? So if you're at a vertex and your neighbors are colored some colors, there's going to be at least one color remaining to you always. So you can just color yourself with that color. But this idea is a little bit difficult to translate into streaming, right? Because you need to look at your neighbors, and your neighbors are kind of not always easy to find in streaming, right? Because the edges can come in any order. So finding your neighbors is kind of hard. However, we do know that delta plus 1 coloring has been solved in the streaming model. So not by implementing the greedy algorithm, but kind of in a different solution. So in this paper a couple years ago, Assadi, Chen, Cornell, they found a delta plus 1 coloring with high probability using a randomized algorithm. And then similar to this, there's been a lot of work actually in this line. So in parallel to that paper that I mentioned before was this other paper that made an O of delta coloring. There's also colorings based off other graph properties, like I said. So the degeneracy of a graph is something a little bit stronger than delta. For things for triangle-free graphs, like I said. And then these last two results are actually going to be here at STOC this year as well. So look out for them. Okay, but then kind of the common thread between all of these algorithms is that they're all randomized algorithms, which is a little bit surprising because for most other problems in streaming, we have deterministic algorithms. So for things like connectivity, minimum cut, all the other things I listed here, we have deterministic semi-streaming algorithms. But then for graph coloring, everything we knew was randomized. So this is a little bit surprising, and we want to kind of investigate why. So we want to see if there are deterministic streaming algorithms for graph coloring. And so I guess one thing I can first talk about is deterministic coloring in multiple passes. So this is a relaxation of the model that allows us to see the data stream more than once. So the stream will come in, and then instead of having to output the answer immediately, we can see it again, and then again, maybe again. But then, so this relaxation has been considered since the start of semi-streaming algorithms. So this paper here is the first paper that introduced the idea of semi-streaming. And then in that paper, they also do multiple passes. So this relaxation is kind of common. And then under this, we get that there are some deterministic streaming algorithms for coloring. And there's a 2-pass semi-streaming algorithm for delta squared coloring and a log delta pass algorithm for delta coloring. And then so the second log delta pass algorithm, has similar ideas to the first result, but then I'll show you the first result in a second. But then, in contrast to that one, we're using a few more passes to kind of build the coloring iteratively, and then get a little bit better bound on the number of colors used. Yeah. So as promised, I'll now show you how to get the delta squared coloring in 2 passes. So the algorithm relies on a lemma. So this lemma says that there's a O of n sized family of coloring functions, so that for every graph, one of these coloring functions creates at most O of n monochromatic edges. So the proof of this lemma is just probabilistic method. I didn't want to go through it here, but I wanted to show you how to use this lemma to get the coloring. So in the first pass, what you can do is, for every coloring in this family, count the number of monochromatic edges. So there's O of n coloring functions, and then counting the number of them uses like log space. So it's perfectly fine. In the second pass, you can fix the C with at most O of n monochromatic edges from the lemma. And the reason you can do that is because, well, you just counted them, right? So you just take the least one. Then you can store the monochromatic edges under C because there's at most O of n of them. And then in the end, you can color these monochromatic edges using delta plus 1 colors because it's a subgraph of the original graph, and then output the product with C to get a delta squared coloring for the whole graph. So that's the end of this algorithm, and it's actually quite simple, right? But then it leaves open still, what about single pass algorithms? All of the randomized algorithms we talked about before in those other papers were all single pass. And then so we want to investigate why haven't we seen any deterministic single pass algorithms for graph coloring yet in the streaming model. And then that's our main result. It's a very strong negative result. And it says that there's no semi-streaming deterministic single pass algorithm that can output even sub-exponential coloring of graphs. So this is actually optimal, right? So to see this in like n logs to the c n space, take 2 cases, right? If delta is small, if delta is less than log to the cn, what you can do is you can store the entire graph because the graph will only have at most n delta edges, right? And then do a delta plus 1 coloring at the end, just like with the greedy algorithm we showed in the beginning. On the other hand, if delta is large, then you can just color every vertex differently using n colors, which is a proper coloring. And it's also, it matches this bound, right? Because n will be exp of delta 1 over c, which matches this bound. So it is a tight lower bound. Before I move on to like how we prove this result, I do want to talk about an independent result that was achieved like at the same time as us, but a little bit different and a little bit similar. So this is like a very strong result for deterministic deterministic graph coloring, and then the result has a little bit weaker bound, so it's a delta squared lower bound, but it's for a stronger type of algorithm called an adversarially robust algorithm. So adversarially robust algorithms can be randomized, but they're algorithms in which, like, even if you have to output the coloring like that you're storing in memory after every step, the adversary can kind of choose to give you bad edges based off like what you're storing in memory. Even if they do that, then you're okay. So so in this kind of well, it's clear that it should be clear that deterministic algorithms are adversarially robust, right? Because if your algorithm is deterministic, it doesn't matter what the adversary does. They feed you some edges. Well, that is some graph that you have to be able to take in and compute with. But yeah, so in the paper they get kind of this this nice result as well. So they also give a delta cubed semi-streaming algorithm, which is adversarially robust but randomized, which is compatible with our result as well. So the upshot is that with these two papers together, we get kind of a nice hierarchy of power of streaming algorithms for this problem. So it shows that randomized algorithms are polynomially more powerful than adversarially robust algorithms, right? Because we had the delta plus 1 in randomized case and a delta squared lower bound in the adversarially robust case. But these are also exponentially more powerful than deterministic algorithms, right? Because we have an exponential lower bound in the deterministic case. Okay, great. So in the remaining time, I'd like to give a proof overview of our main result. And then we'll start with some basic observations. So the first observation is that delta plus 1 coloring is inherently a search problem, not a decision one. So I mentioned this before, but just to emphasize it, we're trying to output like an actual coloring, not just like whether there exists one, right? Because obviously there exists one. And the second observation is like, it sounds very simple, but it's actually quite important. So it says that if an algorithm cannot rule out the existence of an edge, it should not color the endpoints the same. So this sounds kind of obvious, but then what does this mean? Well, I'll show you. So imagine you have these three input graphs, but then they all get mapped to the same memory content by this algorithm, right? So remember, because like you have a lot more different graphs than you have memory, lots of different graphs will be mapped to the same memory content in the end of your algorithm. So imagine like these three graphs are mapped to the same memory content, then the final kind of view of the algorithm that they have to color is going to be the union of these three graphs, right? Because if the algorithm colors like two endpoints the same, like any of these edges in the union the same, then it's one of the input graphs. So they failed to do that input graph correctly. Okay, so this kind of gives us an idea of how to approach this proof, right? So the adversary strategy will just be to create a very dense subgraph in the final view of the algorithm, and then dense subgraphs are hard to color, right? So this means that we need a lot of colors. Okay, so an overall approach, we first reduce the problem to multi-party communication complexity. So this is just kind of to get a better handle of things. So instead of thinking of the stream as one continuous stream, we're going to chunk the stream up into k parts, and then give one part of the stream to every player. So there's going to be k players. And we're going to treat the memory content from one chunk to the next as the message of the corresponding player. So what does this mean? Well, if you think about like these players kind of executing a streaming algorithm, then P1 can execute the algorithm, give its memory to P2. P2 can continue their computation on the memory that P1 left off on. And so if they use the memory of the algorithm as the message, they can compute the result. And so what this means is that any bound on the minimum message size in the communication complexity model is a bound for the storage size in the streaming model. Okay, great. So what inputs do we give to these players now? Well, we want the entire input to be a graph of maximum degree delta, right? So that means we should give each player a random graph of maximum degree, say at most delta over k. So then the union of these graphs will definitely have max degree at most delta. Okay, and then lastly, we're going to define the view of each player. Like I mentioned before, it's going to be kind of the union of all of the graphs consistent with the message that they received. So yeah, it's the union of all the input graphs consistent with the messages that they received. Okay, and then so for example, if the final input graph, which is the union of like the input graphs to the k players, looks like this, then the final view of player k+1, which is kind of just for notation, is going to look something like this. So I mean, this is our goal, right? It's going to have lots of extra edges, and then importantly, our goal is that there's going to be a very dense part of this graph as well. So yeah, okay. Like I said, the plan is to force the final view graph to have a small number of non-edges, and in particularly, at most, n squared over delta z decay non-edges. And the reason we care about this is because you can think of a C coloring as inducing n squared over C non-edges. This is just a Cauchy-Schwarz type argument. And then if you use this with the fact that the view graph has at most n squared over delta to decay non-edges, that means that the view graph cannot be colored with less than delta to decay colors. Which means if you choose k sufficiently large, then you get a lower bound on the number of colors you need that we want. Okay, so what we need to do now is we need to understand how well players can keep track of non-edges through the messages. And then that's kind of going to be the main compression lemma that this paper has. So the compression lemma says that if you start with let's start with the base graph, and then we're gonna take a subgraph of the base graph, and H you should think of as the input to each player. So we're gonna sample H from some base graph, and then this condition that the max degree is at most like 2p times delta base is not that important, right? Because the max degree is going to be that for like most vertices anyway, just by probability. The conclusion is that any compression scheme with S-bit summaries can only recover about S over P non-edges from H. And S you should think of as approximately n, right? It's O tilde n, but you can think of it as just n. And then the idea of this proof is that, well, an S-bit summary can only capture events of probability around 2 to the minus s. But if you calculate the probability of a fixed set of S over P non-edges, that's going to be less. So the S-bit summary cannot capture this event. So this is kind of abstract, right? So we should see how this lemma is used. And then, so let me show you how this is used. We're going to apply this like once for every player. So starting with the first player, G base is going to be the complete graph, and delta base, as usual, will be n-1. We're going to sample H from G base, and then we're going to pick each edge with probability around delta over n. So why is that useful? Well, that means the max degree of G1, sorry, it's a typo, of G1 will be at most delta over k. So down here we're hiding k factors in the notation to make it a little bit more clear. But then the idea is that once you do this, then by the lemma, the message M1 can only keep n divided by p, which is delta over n, which is n squared over delta non-edges. Okay, great. So we now have a bound on how many non-edges message 1 can keep track of. So message 1 gets sent to player 2, and then what happens? For player 2, we set G base to be the non-edges of their view graph. So remember, the view graph is kind of all the edges that are consistent with M1, right? All the edges that G1 could have received consistent with M1. And the non-edges are the things that we still have to kind of give to P2 to try to get them to have lots of edges in their view graph, in the next player's view graph, right? So also remember that message M1 kept track of n squared over delta non-edges, which means that on average there's going to be around n over delta non-edges incident to every vertex. So you can throw away the hideaway vertices, and you get that the maximum degree of this base graph is going to be around n over delta as well. Okay, so we're going to pick subgraph H, just as before. Now we can make the probability of each edge a little bit higher, because this still keeps the maximum degree of the input graph around delta over k. And then that means the message now can keep track of a little bit fewer non-edges. This time it's n squared over delta squared non-edges. So you can kind of see how this is going, right? So I'll draw the picture a little bit differently now. So M2 can only keep track of n squared over delta squared non-edges, which means at most a small fraction of the vertices have more than n over delta squared non-edges, which means so for P3, every vertex here in the smaller subgraph has at most n over delta squared non-edges, which means you can apply the compression lemma as before. We can keep going and going and going. We get n squared over delta cubed here, and then by k times we get exactly what we expect. Right? There's still going to be about n over 2 vertices here because we did not throw away too many vertices every time we made the base graph smaller. And then this final subgraph, there's no way to color the subgraph with less than about delta to k colors. And then that's exactly what we wanted to prove, right? We wanted to prove that any deterministic one-way k-party communication protocol with communication about n cannot find a better than delta to the k coloring. And then so this kind of completes the proof of the main theorem as well. So for some concluding remarks, this was our theorem, just to remind you, our main theorem. But a kind of corollary to this theorem is that various standard de-randomization approaches are not possible in streaming, which is in contrast to many closely related models like distributed computing and MPC. So kind of in these papers, these authors kind of use de-randomization approaches to de-randomize randomize algorithms. But then these things would not work in streaming because, well, we have this very strong lower bound. We have this very strong lower bound for a problem in streaming. And then to leave off, one open question still is we don't know any lower bounds for coloring in 2 passes. So this could be interesting to look into as well. That's all I have to say. So thank you for listening. Thank you.